we first want to know, how did you get into your research field and what's your background?
Well, the background is in computer science and building software. And so I got in mainly because originally I was really interested, when I was a little kid, I was interested in how did ants work, you know, watching insects and things, and all of the organization of how do ants collect food, and
So self-organization.
Self-organization, and how did biology figure this out? You know, if there wasn't if you suspend for a moment the belief that it was all created by an intelligence, you know, could it have emerged on its own from little bits of things that weren't alive that became alive? So it was an interest I had since I was a kid.
The network of SmartLab and the SmartLab ethos help you with your research?
Well, the main thing that it helps me is that I came in with a preconceived idea of what I wanted to work on, and a community of people that I wanted to do it with, and the SmartLab supported that. So when you're normal graduates, more normal PhD programs are fairly archaic for the modern world, in that master's degrees of business and whatnot you have.
So you're very much self-directed, but are there any links to other projects in your research field, or do you know any other experts?
Yeah, there's the Origins of Life field is not a big field, but there's a diverse group of people in it. There are chemists, there are computer scientists trying to simulate these things. There are people in robotics, people studying emergent phenomena, sort of complexity, chaos theory, and that all comes into it. There are philosophers that work in this area. So it's a large international field.
Yeah, you talk a lot about philosophical qualities of your work. How can your research be use of social, medical, or other fields of study?
Well, the philosophical side is one, which is that if in simulation you see something that emerges that some people would call alive or artificially alive, then it's a big deal. You know, is it a real organism or not? What if you made that same organism in chemistry and it's swimming around? You know, is it sourced from the earth, or is it an endangered species now? Does it prove that there doesn't need to be a God? You know, that's a pretty big philosophical question. So that's that side of it. On the other side of it is if you can build a simulator into which something that is biological emerges, you have the power to do that, and you have the power to model the cell and model the cell wall and all these wonderful things and simulate chemistry, and you could potentially solve cancer because you could actually make a model of a cell and watch how, if it's close enough to a real cell, and it might develop cancer under conditions, and you could actually study it. It's like when nobody in their right mind would make an automobile now without building the whole thing on a computer-aided design and engines and this and that. Nobody would do that, but we can't design drugs or medical things. We can't engineer things for agriculture. We're just sort of throwing stuff together and letting the chemistry work, but it's really hard. We don't have simulation tools.
Okay. So talking about simulation, what are your research models, and what computer programs do you use? And do you use DLA models, obviously DNA models, and obviously you use emergent theory and self-organization?
Yeah, the software we're using is any modern software project these days. You don't go and build everything from scratch. You find the best pieces that are out there, and often they're open source. So you grab those, you find the communities that build those, then you extend those. And so that's what we're doing, using GROMACS from Groningen University in the Netherlands, which simulates the movement of molecules around. Then we use other bits and pieces and assemble that, and then you get a much more powerful thing. So that's the software we're using, and that's sort of called agile engineering, or with open source, and it's called molecular dynamics simulation. Is the first where we're starting with.
So you're prototyping, but what is the outcome of the simulation?
Well, the prototype we're building is here's the trick. If you're trying to simulate a little cubic centimeter of water, it would take all the computing in the world running all at the same time to do that. I mean, it's just, well, maybe not that, but it's enormous. No one's ever done that. So you actually have to cut corners. So my PhD dissertation is on an architecture, which I think is new, that will cut the corners to let the simulation, little complex things emerge in the simulation a lot faster within a lifetime of a person, you know, or much less, that we can actually get emergent phenomena to happen faster. And then we'll make a little prototype